and it is convenient, and it's important to make it bigger to view its detail, and that is why the smaller value of y gain setting is helpful, because it enlarges the peak value, but without actually changing its numerical value, it shows us the bigger size. So these are the settings, the time-based setting and the y gain setting. We have looked at both and see what happens to the trace and what is the way it looks when we change the settings. So this is all about cathode ray oscilloscope. Let's move on to another small topic for today. In the AS syllabus, we also come across certain errors when we make experiments, when we make measurements. There are at least two different types of errors which we come across, and those are the two errors about which we have questions in the exam. One of them is a random error, and the other is systematic error. So a comparison is important. The first area in which they could be compared is what this error means and how it arises. A random error is an error which arises due to imperfections of human senses, due to the variations in the natural environment, variations of temperature, movement of wind. That means this is the type of error which arises due to factors over which we have little or no control. So this is that kind of error, the kind of error that arises due to such factors as the imperfections of human senses, movement of wind, or variation in temperatures. So all these are various examples of those factors over which we have little or no control. Imperfections of human senses, the most important example is the timing of the pendulum. Each time you time 20 oscillations, you have slightly different value you get on the stopwatch, even if you're doing it with great care. That means the imperfections of your senses, the quickness of your responses, that is actually not very accurate, and each time you do not get exactly the same time that 20 oscillations should take. And if there are 20 students in the class, every student has slightly different answer. And even if you are doing it with great care, with the same equipment, and you read for several times, it's rare that you have the same answer for two set of readings. So similarly, you can't say that during a delicate experiment there are movement of winds which are affecting your readings, or maybe there are slight variations in temperature which may affect some very sensitive kind of temperature measuring procedure. So whatever error are caused due to those reasons, due to those factors over which we have no control or very little control, they are the random type of errors because they have different values each time. But systematic error, if we compare it with this error and we want to know what is the factor due to which a systematic arises, this is easier because systematic error means there is something which is repeated by the same value due to some kind of fixed error, some kind of permanent or same problem that is recurring in each measurement. So those or that kind of error that arises due to a fault in the apparatus or a mistake or let's say or an error in the procedure that you repeat every measurement that you take. If it is the same fault that is repeated in every measurement, or it is the same error in your procedure that causes the error by the same amount, that is the systematic error. That means it has a fixed value and unlike the random error, we can quantify it exactly. This is the error that we are having in each of our measurements. So if we compare it further, that is actually the next part that makes the comparison even more interesting and more meaningful. The random error may have different magnitudes. It might be larger in one measurement, it might be smaller in the next one. So varying magnitudes. It may have varying magnitudes. Varying magnitude. During one experiment, you repeat different values, you take different values, and let's say there are 6 different readings. So those 6 sets of readings will have varying magnitudes of random error. But if they have systematic errors, they will all have exactly same magnitude in all measurements. Magnitude in all measurements. Then random error may be positive or negative. That means if you are repeating a certain experiment several times, you might have values which are greater than the accurate value. You might have values which are less than the accurate value. So it may have a scatter on both sides. So it might have values greater or smaller than the accurate. Values could be greater or smaller than the accurate or correct value. But in case of systematic error, all the values will be either greater by the same amount or smaller by the same amount. So all systematic errors, all values will be either greater or smaller than the correct value. One particular example which could be useful here, and let me make it here at the top. You are you're trying to hit this target. If the rifle that you are using doesn't have any systematic error in it, you will hit here sometime, or here, or here, or here, or here. That means if you hit it for 5 times, you can see sometimes you have a very close distance from it, sometimes you have a larger distance from it. So it has varying magnitude because it's random. The second thing is your values, sometimes you are on this side of the target, sometimes you are on this side of the target, sometimes you are above the target, sometimes you are below the target. So this is something we mean by it could be smaller or greater than the accurate value. So it could be on either side. But in the case of systematic error, if the rifle that you are using or the bow that you are using has a systematic error, all your appear to be on one side. See, that means there is something wrong with the rifle, because now, although there is some random error, there may be varying magnitude, because we don't expect all of them to be hitting at the same point, even if there is a systematic error. So random error is mixed with the systematic error here. So although they are hitting at different points, but see, all of them are to this side now. That means there is something wrong with the rifle that you are using, and that means they all are greater than the accurate value. That means they are all tend to go to this side. And if you carefully see in each error, you might have all of them might be going to this side by the same amount. So out of this random error, we could find what is the systematic error, by what amount each of this mark is going to this side, and that is the systematic part of it. So systematic error is the same magnitude and same direction. Then another aspect, can we reduce random error? Yes, random error can be reduced. This error can be reduced by taking several readings and then averaging them. But we cannot completely eliminate it. We can reduce random error, but we cannot completely eliminate it. However, systematic error can be eliminated altogether. For example, if we know there is a zero error in vernier caliper, we know there is a zero error in an ammeter or a Newton meter, and we know exactly what is that error, we can fix it, and then systematic error is completely removed. So this is the comparison between the two different types of errors that we have, and they often give you graphs. One last thing in which they will give you graphs and ask you to identify what is the random error and what is the systematic error in it. Suppose you have a very large number of values of the readings taken, and this is the correct value. If you plot a graph between the number of readings and the various values you have taken of them. So this is the number of readings that you have taken, you take on this side, and on this side you take the value against which, for which you are taking this reading. For example, let's say you are trying to find 9.81, the value of G, and you have taken very large number of values in an experiment, and then you plot a graph of all these various values with the number of values you have taken. Let's say this is the shape of the graph that you have taken. This means that most of the values are close to 9.81. So number of n will be large when you are close to this. So this is the distribution of all these values that you have taken. Some of your values that you have taken are on this side. Some of the values you took are on this side. That means there will be a random error here. So a graph of this shape shows that this is not a very accurate experiment. It has a large random error. But if the shape of this graph appears to be this, that means this is a small random error now. So this experiment will be considered more accurate than this one. So this has larger random error, and this one has small random error. Therefore, this will be considered more accurate. And one more thing that is associated with this is also precise. So what does this precise means? If we have very large number of values close to each other, we refer to this set of readings as precise set of reading, and that experiment is known as a precise experiment. A precise value is the one which can be easily reproduced and is very close to the correct value. So this is accurate and precise, and this is not precise. It may be referred to as accurate because this is not entirely wrong, because the main value is large, the number of values that you have obtained is large, many values are close to it, but there are many values away from this value on this side and on this side. Therefore, this may be accurate but not precise. So these are important terms that we need to know. Accurate means close to the accurate value. So if the peak is higher and you have a very small range in which these values are recurring, then it is precise. But If it has a larger spread, then it is not precise because the values are away from the accurate reading. So this is what accuracy and precision is about. So with this, we are closing. Next, we are starting uncertainty day after tomorrow. Thank you.